Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. In Unit 3, we will be studying about heterocyclic chemistry, that is Heterocycles Part 1. In Lecture 1, we will be studying about Introduction Nomenclature of Monocyclic Systems. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The various topics that will be covered in this session include what are heterocyclic compounds, what are the characteristics of heterocyclic compounds, and we will also be studying about the Hantzsch-Widman Nomenclature. In this session, we will be studying about heterocycles. The unit heterocycle will be divided into multiple sessions. In the first session, we will be studying about nomenclature. So, you are already familiar with what is organic chemistry. There are different types. Basically, organic chemistry can be classified into aliphatic, aromatic, and heterocyclic chemistry. So these are all the major three broad categories by which organic chemistry can be classified. And in aliphatic, we have open chain systems and carbocyclic systems. That means compounds containing aliphatic compounds are either open chain or carbocyclic one, that is a cyclic system. And in the case of aromatics, we have monocyclic or polycyclic systems. Benzene, toluene like monosubstituted compounds, everything belong to monocyclic aromatic compounds. Naphthalene and other things are called belonging to polycyclic aromatic systems. The same way in the case of heterocycles, we have monocyclic systems. That means ring containing only one single ring containing one or more heteroatoms, and we also have polycyclic heterocyclic compounds. So these are all the major classification of organic chemistry or organic compounds basically. So let us see about what are heterocycles. Basically, heterocycles are cyclic systems containing one or more heteroatoms. What are heteroatoms? Basically, the heteroatoms are any atoms other than carbon and hydrogen. So the major class of heteroatoms what we will be encountering now belong to nitrogen, oxygen and sulfur heterocycles. Other metal, say for example phosphorus, arsenic and other elements are also possible in the heterocycles, but in this particular course we will be mainly focusing on heterocycles belonging to nitrogen, oxygen and sulfur. They have different physical and chemical properties than their all carbon ring analogues, because when we say cycles, these are cyclic systems. Hetero means atoms other than carbon and hydrogen. So these are very similar to carbocyclic systems. Some of the carbon atoms are replaced by heteroatoms, so they will have different physical and chemical properties. Some of the examples include nucleic acids, pigments, vitamins, antibiotics, drugs, pesticides, dyes, plastics, etc. all belong to heterocyclic compounds. Here we have shown some of the very simple basic heterocyclic compounds. The first one is pyrrole, the next one is furan and thiophene. These are all the 5-membered heterocycles. In the first case we have a nitrogen as the heteroatom, in the second one we have oxygen, and in the third one we have sulfur as the heteroatom. And we have pyridine, which is a 6-membered having nitrogen 1 heteroatom, and we have diazine, in which we have 2 nitrogen atoms. The position is 1 and 4, and we also have 1,3-diazine as shown here. So the 1,4-diazine is another name is pyrazine, and 1,3-diazine is pyrimidine. And we have nitrogen and oxygen or nitrogen and oxygen heterocycles like 1,3-oxalane or 1,3,4-oxadiazole. So these are all the different types of heterocycles. Let us look at the complete heterocyclic chemistry. That means compounds containing heterocycles. They may be classified into various types, and some of the examples are given here. We have RNAs and DNAs. Basically, nucleic acid is one major category that belongs to heterocyclic chemistry or heterocyclic compounds. So in the case of RNA and DNA, we have bases, either it is purine or pyrimidine or the major bases. And when we talk about purine, adenine is one example, and in the case of pyrimidine, we have cytosine as the example. So these are some of the compounds, heterocyclic compounds, which are very important compounds. They form the basis of RNA and DNA. Then we have vitamins, which are vital minerals. That is how the name was given to vitamins. Some examples of vitamins are riboflavin, pyridoxine, folic acid, biotin. All of these compounds contain heterocyclic ring. We have many pharmaceuticals, that means compounds which are used as a drug. Some of the examples include alkaloids, anti-cancer compounds, analgesics, and antibiotics. In the case of alkaloids, some of the examples include morphine and reserpine. In the case of anti-cancer compound, Taxol is one of the very important compound, and camptothecin is another important compound which are used as drugs. And in the analgesic, everyone is aware of desparamine. And in the case of antibiotics, the standard one is a penicillin one. So all these compounds belong to again heterocycles. And we also have hormones like kinetin, serotonin or histamine. These all belong to hormones, and they also belong to heterocyclic systems. And we have various amino acids, say for example prolines, histidines and tryptophan. These are all having aromatic proline is having the nitrogen heterocycle, histidine and tryptophan again belong to nitrogen heterocycles. So these are the different types of heterocycles which are present in amino acids. And we also have pigments, both the plant-based and the animal-based one. In the case of plant-based one, chlorophyll, which is very important for the photosynthesis. And in the case of animal-based pigment, hemoglobin, which is very crucial for our blood. So these two compounds are also belonging to the heterocyclic chemistry. It is not that only these two compounds are there, but there are plenty of other compounds which also belong to the pigment category. And we also have weed killers, basically insecticides and pesticides, which also belong to heterocyclic chemistry. So this particular slide shows the varied type of compounds which belong to heterocyclic chemistry. Let us look at some of the important heterocycles. The first one is plus camptothecin. This has a nitrogen and oxygen heterocycles present in this particular compound. And in the case of the alkaloid reserpine, we have a nitrogen heterocycles present in this compound. And strychnine is another alkaloid. Here also we have nitrogen heterocycle, oxygen heterocycles are present. In the case of epipatidine, again we have its nitrogen heterocycle. Quinine is one another class of compound. Here also we have nitrogen heterocycles. Sildenafil is an important drug which also has nitrogen heterocycles as shown here. 1, 2, 3, 3 nitrogen heterocycles are present in this particular compound. So these are some of the important heterocycles which are used as drugs. We also have oxygen heterocycles as shown here. Most of the oxygen heterocycles shown here belong to a major class called flavones or flavonoids or isoflavonoids. So they have a basic skeleton which is C6, C3, C6 unit. That means there is a 6-membered unit. There is 1, 2, 3 carbon unit, and again another 6-membered unit. So C6, C3 and C6 are the units, and they generally have one heterocycle, that is oxygen heterocycle. Based on how they are connected to each other, we have flavones, flavanol. So flavone is a carbonyl compound, flavanol is enol, and flavonone is again a carbonyl compound. We have flavonols, which are reduced compounds. We have isoflavonoids and neoflavonoids. Their connection only is changed from the normal flavone. So these are various oxygen heterocycles which are generally used. We also have another major class, which is the vitamin B complexes. So we have folic acid, niacin, thiamine, pyridoxine, riboflavin, and biotin. All these are heterocyclic compounds. So there is a vast majority of compounds that belong to heterocycles. Let us compare carbocyclic systems and the heterocyclic systems. We know carbocyclic systems generally contain only carbon and hydrogen, whereas in the case of heterocyclic systems, we have at least one heteroatom. And in our course, we will be studying mainly on oxygen, sulfur, and nitrogen derivatives only. These are present in the ring. And in the case of aromatic systems, we saw aromatic compounds. So aromaticity is an important concept in the case of carbocyclic systems. And in the case of heterocyclic system also, aromaticity is applicable. That means the compounds are generally planar, and they have the 6, that is 4n plus 2 pi electrons, and the stability. So whatever is applicable for normal carbocyclic system, that is also applicable in the case of heterocyclic systems, even though they have heteroatoms. We will also see some of the examples how aromaticity is applicable in the case of heterocyclic systems. And we know carbon does not have a lone pair of electrons. So this is the major character of a carbocyclic system. Whereas in the case of heterocyclic systems, the heteroatoms like oxygen, nitrogen, and sulfur all have lone pair of electron. So the electronic properties of the carbocyclic systems and the heterocyclic systems are quite different because of the presence of lone pairs on the heteroatoms. And ring strain plays some important role in reactivity in the case of carbocyclic system. And in the case of heterocyclic system, both steric and electronic properties play a vital role, because the heteroatoms have the lone pair of electrons. So the electronic property is also very important apart from the steric system, steric strain that is present in heterocycles. Generally, very few carbocyclic compounds are used as a drug, or literally we can say this is not generally used as drug, whereas many compounds are used as drug in the case of heterocyclic systems. And in the case of, even though we say organic compounds are plenty, and the total number of carbocyclic compounds, that is compounds containing carbon and hydrogen, is much less compared to the heterocyclic systems, because we have millions of compounds, known compounds in the heterocyclic system. So comparatively, that is the reason heterocyclic compounds or the heterocyclic system is very, very important for our studies. Let us look at some of the characteristics of heterocyclic compounds. The heterocyclic compounds, basically we have saturated heterocyclic compounds, and the corresponding acyclic compounds will have very similar physical and chemical properties. What does it mean? This is a open chain system. This is a cyclic system. If you look at the number of carbons, 1, 2, 3, 4, 5, 5 carbon unit, one with one heteroatom. This is also 1, 2, 3, 4, 5, 5 carbon unit with one heteroatom. Whether it is an open chain system or a cyclic system, they have comparatively similar boiling point. So in other words, when we say the saturated, because these two are both saturated systems, so the saturated heterocyclic compounds have very similar physical properties. So in the case of nitrogen and sulfur heterocyclics, they have the higher boiling point than similar carbocyclic systems, and in the case of oxygen derivatives, they have lower boiling point. So this is different characteristics you have to know. So this is a cyclopentadiene system, which is a carbocyclic system. Its boiling point is 40 degrees centigrade, whereas when we take the oxygen heterocycle, that is the furan, the oxygen heterocycle, which is a furan, boiling point is 31.3 degrees centigrade. So that means the oxygen heterocycles have lower boiling point than the corresponding carbocyclic one. But in the case of pyrrole or thiophene, the boiling point is much higher than the carbocyclic one. So what is the So in the case of nitrogen and sulfur heterocycles, they have a higher boiling point than the carbocyclic one, whereas the oxygen heterocycle is having lower boiling point than the carbocyclic one. This is a general trend. Then we also have a significant change or difference in properties or reactivity that arise because of the conformational effect or changes and strain effects in smaller rings and changes to molecular shape. So these are very crucial for the heterocycles mainly. So for example, if we take a open chain one ether, this is less reactive compared to the epoxide, which is a highly reactive cyclic system. So the heterocyclic system is more reactive than the corresponding carbocyclic similar analogs. So this is because there is a large strain due to the three-membered ring. So due to that, the strain effect in the small ring facilitates high reactivity of this kind of heterocyclic compounds. And if the sum of the heteroatoms in the saturated systems are substantially more reactive as a nucleophile. So if we take two systems, here we have 1, 2, 3 propyl unit, 1, 2 ethyl unit. So there is a ethyl and the propyl unit attached to the nitrogen. This is a secondary amine. Here we have a cyclic secondary amine. So when we compare the reactivity, these two compounds are having more or less the same basic strength. But when we look at the reactivity as a nucleophile, this unit is a strong nucleophile and it reacts very well compared to the open chain system. So in other words, the cyclic systems are more reactive due to ring strains. Next, we will look at some other characteristics. Here, due to the change in the bond length between carbon and the heteroatom, the heterocycles will have non-uniform bond length. So we know in the carbocyclic system, as shown here in the case of benzene, we have a resonance. And here the carbon-carbon bond length is 1.4 angstrom unit, which is uniform across all the bonds. Whereas in the case of heterocycles, the carbon-nitrogen bond distance is little bit different than the carbon-carbon bond distance. So in other words, we have different bond length in the case of heterocyclic systems. So the CC bond length is 1.3 angstrom and the CN bond length is 1.37 angstrom. So there is a different, subtle difference in the bond length because this happens due to the electronegativity difference between the nitrogen atom and the carbon atom. So in other words, this electronegativity difference between carbon and the heteroatoms, they also show dipole moment. For example, if we take the benzene, which is all carbon unit, the dipole moment is 0 dpi. That means this is not having any dipole moment. Whereas in the case of pyridine, nitrogen is having a lone pair and there is a heteroatom present here, due to which there is a dipole in this particular compound towards this end, that is at the nitrogen end. So this compound is showing a 2.22 dpi unit dipole moment. So the heterocycles show dipole moment due to the presence of lone pair of electrons, or we can also say due to the electronegativity difference also the bond is polarized towards the nitrogen atom. And next, the carboxylic acids and the amides of heterocyclic compounds are all solids at room temperature. So here is an example, niacin, which is a pyridine carboxylic acid. So this is having a very high melting point. The same way nicotinamide, the corresponding amide, also is having a very high melting point. In other words, we can say these two are solids at room temperatures. And the carboxylic acids of heterocycles having ring nitrogen atoms usually melt at higher temperature than those containing ring oxygen or sulfur atom. So in the case, say for example, if we take this particular niacin carboxylic acid, this melts much more than when we have an oxygen or a sulfur analog. So that is due to hydrogen bonding. Now, if we replace one of the CH group in benzene by double bond N to give a pyridine, this introduces an electron withdrawing heteroatom into the ring. So this is the benzene ring. So we are actually removing one carbon and replacing that with a nitrogen atom. So that means the bonds also change accordingly. So when benzene is converted to the pyridine, the whole system becomes electron withdrawing because the nitrogen is more electronegative. So that pulls the electron towards itself. So the ring is depleted of electron density. So in other words, the 6-membered heteroaromatic rings are basically electron deficient, that is pi deficient compared to benzene. So because the nitrogen, oxygen or the sulfur heterocycles are having electron withdrawing nature, or they pull the electron towards itself. So the ring becomes electron deficient. In other words, when we study about the reactivity of these compounds, we will understand what this effect, how this affects the reactivity of heterocyclic compounds. But on the other hand, if we replace two CH units in the benzene by a neutral NR group or oxygen or sulfur, that includes or that introduces electron donating heteroatom. Say for example, we have a benzene, we remove two carbons, that means two carbons if we remove, and we introduce one nitrogen, so that becomes pyrrole. In this particular case, the lone pair of electrons on the nitrogen can be given to the heterocyclic system and make it highly reactive. So in other words, the 5-membered rings with one heteroatom are electron rich, that is pi excessive, similar to benzene. So that is the reason these compounds, pyrrole, furan and thiophene, react much better than benzene in many of the electrophilic substitution reactions that we will be seeing soon. So this is because the lone pair of electrons on the heteroatom is participating in the pi cloud formation. Let us now move on to the nomenclature of heterocyclic compounds. There are various literature references are given here. The work actually started with Hantzsch in the year 1887 and Widman in the next year 1888. They both proposed some ways by which heterocycles can be named, and it was later on expanded by Patterson in a more elaborate way. Patterson contributed a lot of things for the development of nomenclature in the later part, and there is a nice article about nomenclature in advanced heterocyclic chemistry by McNaught, and IUPAC also followed how to name these compounds, heterocyclic compounds. So these are all the various important steps which are taken to give nomenclature for heterocyclic compounds. So since it was started by Hantzsch and Widman, we have the name given Hantzsch-Widman nomenclature methods for heterocyclic compounds. We have simple rules how to name the heterocyclic compounds. This is little bit different when compared to carbocyclic systems, because in the carbocyclic systems we do not have any heteroatom. The functional groups are present in the carbocyclic systems, so they are given priority. So carboxylic acid gets the highest priority and alkane gets the least priority. The least one is the nitro group. So based on the functional groups, the aliphatic and aromatic compounds are named. The similar way in the case of heterocyclic compounds, they are named after the functional groups, basically the heteroatoms. So here the heteroatom is the functional group, and based on which heteroatom is present, the compounds are named. First we need to look at the type of the heteroatom, that means whether it is a nitrogen, oxygen, sulfur, and we also have other heteroatoms, arsenic, phosphorus, selenium, etc. But in this particular session we will be mainly focusing on NOS, that is nitrogen, oxygen and sulfur. And then there is another important thing we have to look into is the size of the ring, that is the ring size that given by number letter N, and then the nature of the ring, that is whether it is a saturated ring or an unsaturated ring. So these are all the three different parameters based on which the heterocyclic compounds are named. And when we give the name, we also have, in the case of aliphatic compounds and aromatic compounds, we have something called the ending name or the parent chain name. That is what is always the suffix. The same way, in the case of heterocyclic compound, the ring size is actually given in the form of suffix, and whatever is the heteroatom that is present is given in the form of prefix. So the type of the heteroatom and the ring size. So the first one is the prefix, the second one is the suffix. That way, if you remember, it becomes easy to give the nomenclature for heterocyclic systems. So as I mentioned, the prefix is always the heteroatom. So what is the prefix we generally give? So we need to identify what is the heteroatom that is present in the system. So if oxygen is present, it is oxa. If sulfur is present, it is thia. And if nitrogen is present, it is aza. So these are all the three prefixes that are included in the nomenclature. So the heteroatom is the prefix which is given, and then the stem, that is the size and the unsaturation, is basically the suffix. So the name ends with the size of the ring and whether it has saturation or unsaturation. Based on that, the name changes. So prefix and the stem or the suffix are the two major class by which the nomenclature is given. So the position of the heteroatom is generally denoted by the ring atom number. So if it is only one heteroatom, we don't give any number. If there is more than one heteroatom present, then we give the position of each the heteroatom, whether 1 2 or 1 3 or 1 4, those kind of things are given. And in the last, we look at the size and degree of unsaturation of the ring, and based on that, the suffix at the end is changed. We will look at each one separately. So here we have shown various ring sizes. So in this particular session, we will be mainly focusing on up to 10-membered ring only, and we may not be focusing more on 7, 8, 9 and 10 because those are not used in large cases. We will be mainly focusing on 5 and 6-membered ring because that is the most common one, and we will also be looking at 3 and 4. So when we look at the number, that is the stem, whenever we say the suffix what we are going to add is given here, and this is derived from the Latin word term. So when this is a 3-membered ring, so for a 3-membered ring the Latin term is tri, and Ra is the letters which are used. So instead of Ra, it is used as IR in the suffix. So when we look at the whole name, we will understand what is the suffix. But just now you remember how it is actually derived. The same way 4-membered ring, that is, we call that as a tetra. The tetra means 4 in Latin. So the ET, the second two letters, is the one which is used as the suffix for 4-membered rings. And for 5 and 6-membered rings, there is no Latin words because uh, in the original papers, they both Hantzsch and Widman had used these two terms, OL and IN. So that is used even now in the same way. There is no change. These Latin names are actually incorporated in the later expansion of the heterocyclic nomenclature for uniformity. So in the case of 7-membered ring, that is hepta. Hepta means 7 in Latin. So EP is the word, the next two letters. So they were used as a EP in the case of suffix for 7-membered ring. And for the 8-membered ring, it is acta. So the first two letters OZ were used directly. And in the case of 9-membered ring, it is nona. So the second and third letter ON is used as a suffix. And for the 10-membered ring, it is deca. So EC is used. So if you look at many of the things, basically the second and the third letters are the one which are generally used from the Latin name for the ring size. So this is the suffix we have to write when we are writing the heterocyclic nomenclature. There are two major classes. One is with nitrogen, another one is without nitrogen. Let us look at when nitrogen is present. So when we have to give the name, the suffix is basically IR, INE. So that means if you look at the suffix, IR is for the three-membered ring. So that is the first two letters. And INE is the unsaturation for nitrogen if it is present. And if it is a saturated one, IDINE. Idin is the suffix that is used for the nomenclature. And if it is a four-membered nitrogen heterocycle, the ET is the stem which comes from the size of the ring, that is a four-membered ring. And if nitrogen is present, there is a last letter E is added to that system, which is unsaturated one. And if it is a saturated one, the first two letters ET remains the same, and we add IDINE. So these are some of the endings which are used in the case of nitrogen in the heterocycle. So if you go carefully, the suffix are always added in the beginning, and the ending is basically based on which type of nitrogen is present. So OL becomes OLE, IN becomes INE. So that means in the last E is added if nitrogen is present. And when nitrogen is absent, that time also the E is missing in many of the cases. But in the case of EAT and OLE, that last E is actually retained, but in all the other cases, the E is not present between nitrogen and whether nitrogen is present or nitrogen is absent. So this way we can actually name the heterocyclic compounds. We will see some of the examples to understand how it is actually done. So we will look at the general stem rule as an example here. So we have a three-membered ring. It is an unsaturated ring. So oxygen is the heterocycle. So this is the prefix that is added for oxa, and this does not have nitrogen. So we simply use the stem word irene. So oxa plus irene is oxirane. So that is the name given here. And if it is sulfur is present, the prefix is thia. So irene is thyrene. So this is the name for this particular compound. And when we go to the four-membered ring, you see here the suffix IR is representing the size of the ring. So that is what is the first two letters. And the ENE is for the unsaturation. So we have an unsaturation, so ENE is added. And OX is nothing but the prefix of the heteroatom. What is the heteroatom? Based on that we had given. So that way we can actually name the heterocyclic ring easily. And in the case of four-membered ring, we have oxa. And if it is four-membered tetra, that remember the word tetra, so ET is the suffix we have to add. So that is the ET added here. And if it is unsaturation, we add one more ET. Here, one important thing which comes up mainly for the four-membered ring, because this is not a completely reduced system. So whenever we are going to name a heterocyclic compound, when we say unsaturation, unsaturation means the ring is completely reduced, double bond is having. So that is what is very important to remember. In the case of four-membered, there is always going to be one CH2 group. Whereas in the case of five-membered ring or the three-membered ring, these two carbons are basically CH carbons. So that means we have a CH carbon here, another one here, another one here, another one here. So four CH carbons are there in the case of completely unsaturated system. And in the case of a four-membered ring, we can only have one unsaturation. That is, only one double bond is possible. This carbon remains like a CH2 carbon. So because of that, in which position the hydrogen is present, we give the number. So this is in the, if we start from the heteroatom number 1, we can number this like a 1, 2, 3, 4 or 1, 2, 3, 4. Generally, we have to give the lowest number for the saturated carbon. So that is how the nomenclature is given. So in this particular case, if we go through this way, we have the second carbon having the hydrogen atom. So that is why the H is given here. So the second carbon having hydrogen atom is written as 2H oxytate. So that is how the compound's name is given here. if it is a thioring, then thia plus ete, the second carbon is the saturated one, so 2H thiate. So this is the name given to this particular system. And in the case of 5-membered ring, we have 1, 2, 3, 4. All the carbons are unsaturated carbon. So oxa plus OLE is the suffix. OL is for the 5-membered ring and oxa is for the heteroatom and E is for the unsaturation. So when you put all the three together, we have oxole as this compound and we have thiol for this particular compound. These are the IUPAC nomenclature. Of course, for these two compounds, we have a common name, and in many cases, we generally use the common name and we do not use the IUPAC nomenclature for 4-membered, 5-membered or 6-membered rings. And when we have to give the saturation, basically the lowest number is given to that carbon as a NH as shown here, or we can also write N, N plus 1 dihydro tetrahydro, like that we can actually give that name. So that means this carbon is a dihydrocarbon. So those kind of things also we can actually write. And in the case of saturated systems, there is no double bond here. So this is oxa plus IR for the 3-membered, ane for the saturated one. So this compound name is given as oxirane. And if it is sulfur, thia for the sulfur and IR for the 3-membered, ANE is for the saturation. So we give the name thyrene. And in the case of 4-membered ring, this is basically oxa is for the heteroatom, ET for the 4-membered, ANE for the saturation one. So like that we can actually extend the name for any number of heterocyclic systems. In the case of 5-membered, if you look at, this is 5-membered, so we have OL, this is oxygen, so we have oxa, and this is a saturated one, so ANE. So oxa plus OL ANE, we call this compound as a oxalane. And if you carefully look at in all these cases, the last alphabet is actually dropped in most of the cases. So this is how we actually write the name for these heterocyclic compounds. And when we go to nitrogen heterocycles, so here the rule is also very similar to what we have seen. Only the difference is what is the ending that keeps changing for nitrogen and non-nitrogen heterocycles. So nitrogen is given as aza and IR is for 3-membered. INE is the ending for the 3-membered unsaturated system. So aza plus irene, azirene. So the A is dropped when we write the name. The same way, if it is a saturated one, instead of INE, it is IDINE. So this becomes aziridine. And in the case of 4-membered also, here we have a saturated carbon. So this is written as 2H. And the completely reduced one is written as acetidine. And if it is a 5-membered nitrogen heterocycle, the actual IUPAC nomenclature is azole, but we call this compound as a pyrrole, which is a common name. And this is pyrrolidine, which is a common name, and an IUPAC nomenclature for this compound is azolidine. So this OL, these two letters belong, or they show this is a 5-membered ring, and AS shows that this is a nitrogen heterocycle, and IDINE shows that it is a saturated ring. So that way we can easily write the name, the structure of the compound from the name also. Always you have to look for the first letter, that is the prefix. The prefix tells what is the heteroatom present, and the next two letters show what is the size of the ring. So A is that means it is a nitrogen heterocycle. ET means it is tetra, that means 4-membered heterocycle, and IDINE means it is a saturated nitrogen heterocycle. So from this name also we can draw back the structure of this particular compound. The next important thing is, if there is more than one heteroatom in the ring, so how are we going to name them? So in this particular case, when more than one heteroatom is present, the order of priority is oxygen, sulfur and nitrogen. So there are two major rules we have to remember. The base name, when there are more than one heteroatom is present is based on nitrogen. So the base name, when we study, we will see what does that mean. So the base name is basically based on nitrogen atom, and when we have to give the numbering, oxygen gets the priority followed by sulfur, then only nitrogen is numbered. So if there is only one heteroatom, we can start the heteroatom number from that itself. So furan, the number oxygen will get 1, and in the case of pyrrole, the nitrogen will get the number 1. And in the case of pyrimidine, we have to give any one nitrogen the lowest number, followed by in the clockwise direction which gets the lowest number here. So this nitrogen gets the number 1 and this nitrogen gets the number 3, and if they are next to each other, 1 and 2 are the numbers which we can give. And when there is only one nitrogen, we don't have to worry about that. Same way in this particular case also it is 1. But if we go to heteroatoms nitrogen and oxygen, as in this particular case, so which one will get the lowest number? Either the nitrogen gets or the oxygen gets. So the priority always given is oxygen gets the highest priority. So this is given the lowest number, followed by the next heteroatom nitrogen. So the numbering goes from 1, 2, 3, 4, 5. The same way, if you look at this compound, this oxygen is having the lowest number. If you go from this clockwise direction, 1, 2, 3, 4, the number what the nitrogen gets is 4. But if you go in the counterclockwise direction, the nitrogen gets the number 3. So the least number should be given to the next heteroatom. So the numbering is given as 1, 2, 3. And when nitrogen is instead of oxygen, if sulfur is present, that also gets the priority before nitrogen. So this is numbered as 1 and the nitrogen is numbered as 2. So this is how you have to remember in the numbering of heterocycle. The rule followed is oxygen followed by sulfur followed by nitrogen. And the third one, we saw about the ring size. We also saw about the heteroatom. Now we will see about the saturation. So whenever there is a saturation, the saturation is given the least number and followed by H and the name is given. So in this particular case, we start from this is the saturated carbon. So this is the nitrogen. So when we have to number this saturated carbon, we put this as a 2H pyrrole. So that way we know the second hydrogen is a saturated hydrogen. And in this particular case, we know the numbering, the sulfur gets the lowest number followed by the nitrogen. So this is 1, 2, 3. So the second carbon is having the hydrogen. So we write this as a 2 hydrogen, 1 and 3. Thia, first heteroatom is the thia and the third heteroatom is as. So Thi means for sulfur, AZ is for the nitrogen, INE for the 6-membered ring. So IN is actually for the 6-membered ring, E is the ending. So with that we can actually tell this is a 6-membered heterocycle containing sulfur and nitrogen. And if you look at this compound, this is a 7-membered ring. So in this particular case, the nitrogen gets the, because there is only one nitrogen, so this gets the lowest number 1, 2, 3. The third carbon is having the hydrogen atom, that is the saturated one. So this is written as 3H, and this is a nitrogen heterocycle. So we write AZ, and 7-membered ring is hepta, HEPTA. So the next, the first two letters is EP. So this EP talks about this is a 7-membered ring. And this INE is the ending for the nitrogen heterocycle. So this compound is named as 3H-azepine. And this one we have 2 nitrogens are there. You can start from 1, 2, 3, 4, 5, or you can start from here 1, 2, 3, 4, 5. In either case, this carbon is saturated carbon is 5 only. So 5H is the number given to this saturation. And 1, 2, there are 1 and 2 positions, nitrogens are present. So 2 nitrogens are there. So we have di, and these are nitrogens. So we have AZ, and this is a 7-membered ring. So like EP, hepta, we have EP, and this is a nitrogen heterocycle ending with INE. So that way we can also give the name for this compound as 5H12 diazepine. So these are all the ways by which we can number the various heterocyclic compounds. Here we will be looking at some of the common names of the heterocycles. So this compound, even though is given oxygen, the blue colored one are basically the IUPAC nomenclature, and the black colored one are the normal common names. And most of these compounds are generally represented by their uh, common names only. They are not generally used using the IUPAC nomenclature. So this is generally called as ethylene oxide. This is called ethylene amine, and this is trimethylene oxide. This one is a very standard compound. We generally use furan. Although the IUPAC nomenclature is oxole, we generally call this compound as a furan, and this is a solvent which generally people use, which is a tetrahydrofuran. Although the IUPAC nomenclature is oxalane, you will not see this oxalane as a name in many of the publications. People prefer to use this as a tetrahydrofuran also only. The same way thiophene, pyrrole, pyrrolidine, these are all the common names you will be encountering in many of the literatures and other places. So the common names for these heterocyclic compounds are still in use, and their IUPAC name is not generally used. The same way, if you go with dioxane is a solvent, morpholin is a base, and pyrimidine, imidazole is a base, piperidine is a base, pyridine is a base. So these are all the different compounds which are generally used in their common names only. You can remember this IUPAC nomenclature for the sake of knowing, but generally most of the compounds shown here are basically given in their common names only. Let us look at some of the rules that we have to follow when we are naming heterocyclic compounds. There are various things we will be encountering, that is permutation combinations are possible. We will work out at least most of the permutation combinations to see how we can name the heterocyclic compounds. The first one is like if there are two rings and they have the same heteroatom but their size is different, then which one we have to actually make as the base unit. So we have a 6-membered unit, we have a 5-membered unit. So we have two rings are there, the heteroatom is same, nitrogen is the same heteroatom. So which one will be considered for the base? That means whether this is going to be having a 6-membered ring IN and this is a 5-membered ring, it will be having that prefix OL, suffix OL. So whether it is a OL or IN, that is the major thing we have to see. So in that case, we have to choose the larger one. So this is a 6-membered ring. So this compound is basically named as a piperidine ring, that is a 6-membered saturated ring. The next one is we have two rings having the same size but they have different heteroatoms. So in that case, how do we name them? We have a 6-membered, another 6-membered, we have a 5-membered and 5-membered. So how do we name these things? So in this particular case, we have to choose the heteroatom having the highest priority. So in the case of heteroatom having the highest priority, it is nitrogen which is having the highest priority, followed by oxygen, followed by sulfur. So this is N and O are present, both are 6-membered ring. So this nitrogen will be, this particular compound will be named as the nitrogen as the base, that is a 6-membered ring. And in this particular case, the oxygen will get the base because oxygen has the highest priority compared to sulfur. So the next one is both the rings are having same size but contain different number of heteroatoms. In some cases there is only one heteroatom. In another case we have two heteroatoms. So in this particular case, this ring has one heteroatom, this ring has two heteroatoms. So when there are more than one heteroatom, the highest number of heteroatom becomes the base unit. So based on that, we are going to name this particular system. So nitrogen and oxygen are present in one single 6-membered unit. So this is like a morpholin system. So the compound will be named after morpholin. And this one is having nitrogen and oxygen. So this is oxazole. So this compound will be named as a oxazole unit. So this is how based on the number of heteroatoms or the size of the heteroatom or the priority of the heteroatom, we can choose the heterocycle's name. The next one is two rings are having the same size and the same number of different heteroatoms. So in this case we have two heteroatoms. In this ring also we have two heteroatoms. So the ring size is same, 5-membered ring, and the heteroatom is also same, 2. So in that case, which will be named as the base unit? So in this particular case, the priority goes to oxygen compared to sulfur. The highest priority is nitrogen. So since nitrogen is present in both the units, so we can just go to the next highest priority group. Oxygen is the next highest priority group. So this ring is considered as the base unit. So the compound will be named after oxazole unit. So this is how we can have multiple permutation combinations for naming of heterocyclic systems. And the next one is, if the two rings have the same number, that is the same size, and also have the same number and the same type of heteroatoms. So we have two rings. One ring is having 2 nitrogen. This is a 6-membered ring. This is having 2 nitrogen. Another ring is also having 6-membered ring having 2 nitrogen atom. So the ring size is same, the number of heteroatom is also same. So in this particular case, which will get the priority in naming? So in this particular case, we have to choose the ring with the lower number. That means if we start to number this compound, we will start from this nitrogen 1, this nitrogen will become 2. In this particular case, if we start from any of the nitrogen 1, 2, 3 and 4, so this is going to be a 1,4 disubstituted system. This is 1,2 disubstituted system. So the lowest number is given to the 1,2 disubstituted system, and hence this compound is named as a pyridazine, that is 1,2 disubstituted nitrogen. This becomes the base for naming this particular compound. So these are all the various different types of combination that is possible for numbering heterocyclic systems. Here some examples are given for the bicyclic systems. So as I mentioned, always we have to take the nitrogen containing heterocycle as the base unit. So this is nitrogen heterocycle. This is called indole. And here we have sulfur, here we have oxygen, we have only one heterocycle. So they can be named after the corresponding heteroatom only. In this particular case, we have two heteroatoms are present. Here again, two heteroatoms are present. So when multiple heteroatoms are present, two things we have to follow. One is, what is the base unit for that particular system? That is the heteroatom priority is 1. The second one is numbering. So which one will get the lowest number? So these are all the two things we have to remember when there are more than one heteroatom is present. So in all the cases, whenever nitrogen is present, nitrogen is always considered as the base. That means that is the system is named after the nitrogen heterocycle only. That is getting the highest priority, followed by oxygen, followed by sulfur. But when we are going to number, oxygen gets the lowest number in all the cases. So in this particular case, we have nitrogen and oxygen heterocycle. So the ring should be named after the nitrogen. So that means this is a oxazole, oxa, that means oxygen is present, and azole for the nitrogen that is present. So OL is basically for the 5-membered ring, because this is a 5-membered ring. So the OL is for the 5-membered ring. So if we look from this oxazole unit, this is basically the 5-membered unit having nitrogen and oxygen. So how do we number this? The oxygen gets the lowest number, that is the number starts with 1 on oxygen, followed by 3 on nitrogen. And we also have a benzene unit attached to this one. So this is benzoxazole unit. So this compound is basically named as benzoxazole. And if this is 1 and 3, nitrogen and sulfur are present, again after oxygen, the sulfur is the one which gets the highest priority in the numbering system. So sulfur gets the lowest number followed by nitrogen. So this is a thia unit, that means sulfur is present. So the same similar to the oxygen heterocycle, we have the sulfur heterocycle which is named after benzothiazole. And the position is 1,3. This is a 1,3 benzoxazole, and this is 1,2 because the numbering is here in this particular case it is 1,2. So it can be named as 1,2 benzoisoxazole, and here this is given as 1,2 benzoisothiazole unit. So this is how these compounds can be named in the bicyclic systems. So the oxazole units are basically 1,3 units. So generally when we are writing as 1,3 unit, we do not write the 1,3 number here in front of the heterocycle's name. Here there are some heterocycles which are given. The black ones are basically the common names, and the other IUPAC nomenclature is given here in this bracket. In summary, let us recap what we have studied so far. We have studied about what are heterocyclic compounds. A cyclic system containing heteroatoms, mainly oxygen, sulfur and nitrogen. What are the characteristics of heterocyclic compounds? Basically their physical and chemical properties, their dipole moments, and we also studied about the Hantzsch-Widman nomenclature. So what is the general stem rule, what is the prefix and suffix usage, and how to number the heterocycle. So these are all the things we have studied. With that, we conclude this session. Thank you.